convention for potentials. I mean that in the Jackson book you'll find this formula with the minus sign here. So let's keep with the conventions and define the potential like that. Okay. So to conclude, there is a local symmetry in the Maxwell's equations. And the local symmetry has sort of different applications, different interpretation, physical interpretation. This simply tells us that A mu and A mu plus d mu omega, they describe one and the same physical reality. So the electric and magnetic field defined with these two potentials will be the same, and so electric and magnetic fields are the only observable. So this is the only quantities that we can measure. Okay. So if you imagine a space of all fields, so this huge space, right? So it's a point in this space is a distribution of A in space and time. Then gauge transformations will slice the space into orbits. So each line here is a set of fields that differ by a gauge transformation for all omega. So this is called a gauge orbit. And so each of these orbits corresponds essentially to one point. So there is a redundancy in description, and the physics only depends on orbits, not on the field configurations. So the way to proceed, so one way to proceed is to pick one point on each orbit. So we draw a horizontal line that intersects each orbit once. And so this and this way it picks one representative from each gauge orbit. So picking up this horizontal line is called gauge fixing. And of course, there is huge arbitrariness in this procedure, so we can choose any line we want. Okay, the only condition is that it intersects each gauge orbit only once. So one particular way to choose this horizontal line is by imposing a gauge condition with some function. So we can say that some function of their potentials and their derivatives is equal to 0. So this would be our gauge condition. The independence, and then we should make sure that this indeed picks one point on each intersection, okay? So as such function, we can take, well, potentially anything. So there is a variety of gauge fixing conditions that are being used, and they're more useful in one situation and less useful in the other. So for our purposes, we would like to make a gauge fixing in a way that wouldn't break Lorentz invariance. So one possibility for such a for such gauge fixing condition is to say that the gradient, well, the divergence of A is 0. So this is a gauge fixing condition that we will choose, and this is called, well, this is, I think this is called the Lorentz gauge. So Lorentz gauge actually doesn't fix the gauge freedom completely, because if you shift A mu by A mu plus D mu omega, and then suppose that this satisfies the Lorentz gauge condition, then the transformed field will also satisfy the Lorentz gauge condition, provided that omega is has so the D'Alembert operator acting on omega is 0. So this, we still have some residual gauge freedom. Okay, so now what we need to do is we need to, we are now ready to solve the Maxwell's equations. So we need to take this formula for F mu. It will immediately solve the second equation. We substitute it to the first Maxwell's equation, impose the Lorentz gauge condition, and the resulting equations that we get are very simple. So these are Maxwell's equations in the Lorentz gauge. So actually, this just looks like 4 set of Klein-Gordon equations with mass 0, right? And we know how to quantize the Klein-Gordon equation. So we just write the same expression for A. But okay, let's first talk about just classical equations of motion. So we know how to solve the Klein-Gordon equation, and we can just do it here for each component of A separately. So the solution will be a set of plane waves. And then, in principle, we could have written just this expression for all mu. Instead of doing this, so we would get amplitudes would have an extra index, right? So they will be parameterized by p, and we'll have an extra index. What we want to do is we want to sort of change a basis at each particular p. So we write this as epsilon mu s of p, and then times as. These are some particular sorry. So these are vectors in the momentum in the space of potentials, which form a complete basis. So mu runs from 0 to 3, so S will run from 1 to 4. The reason we want to do it is that we want to choose bases differently at different values of momentum. So, and in principle, we can choose these vectors to be complex. So then this term should say the field is real. So this term will be complex conjugate to that one. Well, if this really were 3 or 4 scalar fields, that would be it. But now we should take care of the gauge invariance. So first of all, we need to impose the Lorentz gauge condition. Yes?
You enumerated the mu and s. It looks like mu corresponds to the ordinary space-time coordinates.
Yes.
What is it that s enumerates?
Just a second, I'll explain. Okay, so we need to impose gauge. And then you see that d mu, when acting on e to the minus plus ipx, gives minus plus ip mu times minus plus ipx. So what happens when we differentiate this solution to the equations is that we will find that this E, this vectors epsilon s of p, they're multiplied by p. Okay? And so the gauge condition will be equivalent to the orthogonality of these epsilons to the momentum for vector. So what we have is that at each point, so suppose that p is fixed. Then we have we choose some basis of 4 vectors, epsilon 1, epsilon 2, epsilon 3, and epsilon 4. So they have to form a complete basis at each point. But you see that the gauge condition prescribes us to choose this basis in such a way that, we should exclude the amplitudes that correspond to the longitudinal modes that are perpendicular to the form momentum. Oh, sorry, I got confused. So so this condition picks up the physical polarization of our waves. Okay. So and you see that the physical polarizations should be perpendicular to P. So therefore, it is convenient to choose the basis in such a way that some of this polarization, well, vectors will be physical and some unphysical, according to how they satisfy, according to whether they satisfy this condition or not. And of course, this condition depends on momentum. So the basis that we choose at different P, well, they are different. They depend on P. So let's see what are the solutions to this equation. So there is one obvious solution. Yes.
How does the equation that represents the gauge condition follow from our observation about the derivative of the exponential?
So I need to impose the condition that d mu a mu is 0. And then I have an expression for a mu. So I have to differentiate it in x. So the only places where x appears is here and there. So when I differentiate this in x, I get minus ip mu that multiplies this, it contracts with this index on epsilon. The same is here, but the epsilon is also the same. So the derivative will vanish if that condition is satisfied. Well, let's consider an example which probably will clarify what we should do. Is namely, let's consider electromagnetic wave moving in the z direction. So this will be the momentum will then have components 1001 and then times the frequency. So then we can immediately see that vectors epsilon 1 with components well, any vector sitting in this direction, so that has 0 time-lag component, and whose spatial components have no z component, have no z, well, are directed are sitting in the xy plane, will immediately satisfy this condition, and well. What we will do, we'll choose the vectors that have components 1i, and then epsilon 2 we will choose to be a complex conjugate to epsilon 1. So this will have components 0, 1, minus I, 0. So the claim is that this describes circularly polarized electromagnetic waves. Okay, then, well, then to form a complete basis, we need to add vectors, 4 vectors that have components in z direction and in time direction. And so one possibility is to take epsilon to be, well, to have these components, Um, and then has to have these components, okay? Yes?
I'm trying to see how E1 and E2 describe circularly polarized waves. I thought that they should depend on time.
Time dependence sits in here, so in this oscillating exponentials. So you'll do an exercise in tutorials which will, remind you how it works. So let's see. So this is just proportional to p mu. Let's simply equals to p mu divided by omega. And then we have an equation that p mu is 0. So this vector is also okay. So it satisfies the gauge condition. This satisfies and this satisfies. But this vector does not. So this one we should exclude. So as expected, the gauge condition, so it is one equation, right? One equation on one function. It eliminates exactly 1 degree of freedom out of 4. But, it doesn't fit really well with what we know, because electromagnetic waves should have 2 polarizations and not 3. So how does the other degree of freedom disappear? Well, the reason is that there is this residual gauge invariance. So we are free to add or subtract any gradient from this function under the condition that the Lambert operator acting on this function is 0. So the claim is that this vector corresponds to a total derivative. So again, so this omega is not the same as this omega. Sorry for using the same letter for different quantities. How to see this? Well, this polarization vector is proportional to the momentum. So if you write p mu here instead of epsilon p mu here, then this is the same as we can replace them by x derivatives acting on the exponentials, and then take out this derivative outside of the Fourier integral. And also what remains will be some complicated function of x, but this function will satisfy the Lambert equation just because of we imposed the on-shell condition here. So this gives a total derivative and is eliminated by residual. So we can eliminate it by residual gauge transformations. In other words, so to conclude, the amplitude with this polarization should not be present. It does not satisfy our gauge condition. The amplitude with this polarization can be set to 0 just by adjusting, by adding an appropriate gauge function to our potentials. So what are left are these two polarizations that describe transverse electromagnetic waves. Well, if you were to choose the normal basis with 1 here and 0 here, and 0 here and 1 here, that would correspond to linearly polarized waves. So for some reason, it's more convenient to choose circularly polarized waves. This is, at the end, is a matter of convention. Okay, so well, we can always do the same for any p. So if we have um, an arbitrary electromagnetic wave moving without arbitrary momentum, we choose some 3 vectors, epsilon1 and epsilon2, which with epsilon2 being complex conjugate of epsilon1. And so E mu of P E mu1 will be equal to 0 E1 epsilon 2 will be 0 E2. So this describes physical propagating waves. And in addition, there will be epsilon 3 mu proportional to P mu and epsilon 4, which for which P mu epsilon 4 mu is not equal to 0. And then these 4 vectors form a complete basis in the 4-dimensional space, and they depend on P. And so, if we were to solve the classical equations, the classical Maxwell's equations, it will be enough to keep just these 2 polarization vectors. So, with these 2 polarization vectors, this would be the solution for the Maxwell's equations. And this solves the problem of how electromagnetic waves propagate in the vacuum, right? I suppose you have seen this solution in this or that form in other courses. Now, well, and then we want to quantize this picture. And how do we do that? Well, we promote these amplitudes to creation and annihilation operators. So we say that A and A dagger are creation and annihilation operators. Delta SR, delta of P minus Q. And so when S and R are equal to 1 and 2, these operators describe 2 helicity states of a photon. So it can have helicity +1 or -1. and some for momentum. So with the help of these operators, we can generate a Fock space, and that would all be very good. But unfortunately, this will not really be consistent. And the point is that in keeping only physical polarization in an equation like that, we impose a functional equation on A. Okay, so we just say that d mu A mu is equal to 0 is a function. For a function, that's okay. I mean, we can solve this equation by keeping only the right polarization vectors. But if you have an operator, setting it to 0 is really not a good thing to do. So unfortunately, we cannot set so we cannot impose this condition on an operator. Is inconsistent if interpreted as an operator equation. Well, why is that? Instead of really trying to explain it in this context that we want to study for electromagnetic field, let me give you a simple toy example from basic quantum mechanics. Suppose we consider a particle, and let's just consider a particle on a plane that moves in some potential that depends only on one of the coordinates. And now we want to consider the states of this particle that only move in one direction. So they, say, oscillate in this potential and do not move in the direction x2. So in classical mechanics, we can simply say that the momentum in the vertical direction is 0. And so this will describe the motion of this particle along x1. Okay? So this is a consistent way to say that we want only to study particles that do not propagate in x2. Now in quantum mechanics, this equation will not be consistent. Just because we have, although we don't have a coordinate x2 in the Hamiltonian, sort of in the back of our mind that we remember that it exists and it satisfies the canonical commutation relations. So, well, the right edge part here. So we cannot set an operator to 0 without violating this commutation relations, right? So it's impossible to set. So this makes So what do we do? Well, the way to proceed, of course, is to so this equation tells us that p and x cannot be measured with simultaneously with 100% degree certainty. So if we know for sure that the particle has 0 momentum, then we have to admit that we know nothing about its coordinate. So it is spread out in the x2 direction with probability 1 to find it at any point. Okay. So the way to impose this condition is that we impose it on our states. So we say that we are interested in the states that satisfy this condition. And so this condition now is not a condition on operators, but a condition on states. So which simply means that our wave function will be independent of x2. So this means that psi will be psi of x1 and not of x2. So returning back to electrodynamics, this suggests that the gauge condition should not be imposed as a condition on a mu, but should rather be imposed as a condition on states. So we pick our physical states by saying that the physical states are those that are annihilated by the Lorentz gauge condition. So this defines some subspace of the full Hilbert space. So we have to introduce the unphysical oscillators, which are time-like and, well, which are longitude. We have to introduce longitudinal and time-like oscillators, but we eliminate them by saying that our physical states satisfy this condition. Okay. And so the quantization that proceeds in exactly the same way. So we have 4 oscillators instead of 2. But in the states that we want to study, so the physical states, only particles that correspond to physical photons can be present. Now, then you may say, why at the end we came to the same answer, right? So our physical states are photons with these two polarizations, and the oscillators that are present here but do not satisfy this condition of physical state, they will never appear. Which is true as long as we consider free electromagnetic field. So in the next step, we'll see how electromagnetic field interacts with electrons and positrons. And there it will be important to keep these unphysical polarizations, although they will never appear in the physical states of the theory. When we'll study perturbative expansion, that anyway, so they will appear as intermediate states in the calculations that we will do. So they never appear as physical states. They don't describe any particles, but they may appear in intermediate states. So I guess I'll stop here. Thank you.